Good morning, gentlemen and ladies. We want to start the lecture. Let's have some revision. In our last lecture, we looked at the effects of negative feedback on the gain of the amplifier, and we took some examples. If you recall, we look at the examples starting from page 456. Now, I want to briefly go over the examples again, then we continue today's lecture. Now, to check, you can see on the screen that I have the example page open. You see it now. The example page is open. Yes. You look at the examples. That negative feedback reduces the gain of the amplifier, but increases stability. That is the point there. We checked some calculations. We did some calculations under that as well. Now we also looked at the effect of negative feedback on distortion. Effect of negative feedback on distortion. And we derived this formula that we have here, that negative feedback reduces distortion by a factor of x, which equals 1 divided by 1 plus beta A. That is the effect with which negative feedback reduces, the value with which it reduces the distortion of an amplifier. A fraction of 1 plus beta A is the amount, the fraction by which it reduces the gain. Okay, we want to look at another example now, example 5. Not sure whether we have handled this example 5 before. Let's look at it again. An example, an amplifier has a gain of 1005% distortion with an input signal of 9 volts. When 9 volts input is applied to the amplifier, calculate 1. Output signal voltage, 2. Distortion voltage, and 3. Output voltage. Now, if you look at this, VOS, that is the output signal voltage. So number 1, signal output voltage is VOS, that is A multiplied by VI. And the A is given there as 100. A is given as 100. And the question here, there's a typographical error. The input voltage is 1 volt, not 9 volts. So you can change that in your notes. This one is 1 volt, 1 volt, 1 volt, not 9 volts. So you can change that one in your notes. Okay. I know you are listening to the lecture. The lecture has started and then I'm recording it. I'm going to give you the video later on for those that will not be able to attend today. Okay, so that example there, the input voltage applied is not 9 volts. That's what I was just trying to say. So you check your own notes, that page, change that value to 1 volt. It is not 9 volts. I want to see the word file I have here to actually correct from the word file whether the error is still there. Okay. Right? So, but apart from that, the solution there is A multiplied by VI. That's the solution to that problem. VI is 1 volt, and A is given as 100. So for that reason, the answer is 100 times 1. That is 100 volts. 100 volts. That is what we should have as the answer. But if you look at the value given in the question, you realize that you could not get 100 if you use 9 volts given in the question. You use the 9 volts given in the question, as we have it here, you cannot get 100 here. This one is correct, but that 9 is wrong. Right? Let's look at the number 2, distortion voltage. Distortion voltage is DVO. DVO. D is the value of distortion. VO is the output voltage. So let's see the solution to that now. Distortion voltage equals 0.05 because we are told that we have 5% distortion. So that is 0.05 multiplied by V output. Output that we just calculated is 100 volts. So the answer is 0.25 times 100. That is 5 volts. The answer is 5 volts. Okay. So 5 volts is the distortion voltage. Then number 3, we are told to calculate amplifier output voltage. Amplifier output voltage is equal to V output plus D. That is output voltage. Output signal voltage plus distortion voltage. That is 100 plus 5. And the answer is 105. 105. Okay. So we see that solution there is very simple and straightforward. Very simple and straightforward. But at times, when you are given such a problem, you have to know what you are doing. You don't want to be unnecessarily confused. So if you look at this word file now, it is 1 volt. The word file, the old one, the old PDF file shows 9 volts, which was wrong. So that's why I had to bring out this word file. Now, let's move on to this new subheading. Effect of negative feedback on bandwidth. Bandwidth of an amplifier or any other electronic device is regarded as the difference between the maximum and minimum frequencies that the device is working with. So sometimes we call it corner frequencies, or 3 decibel frequency, F1 and F2. So the structure of the a graph that we have here will help us to understand what effects does negative feedback have on the bandwidth of an amplifier. We have the graph of gain against frequency. So if you look at the screen now, you see the gain A up here, the gain A up here, around here. The axis here is gain, and then the independent axis here is frequency F. Now this is the first frequency, first corner frequency F1, and this is second corner frequency F2. So the difference between these two is the bandwidth, BW. It's represented as BW. So if you look at that, by calculation, we could say BW equals F2 minus F1, whereas the F1 is lower 3 decibel frequency, F2 is upper 3 decibel frequency. If A is the amplifier gain, then the gain bandwidth products, gain multiplied by bandwidth, will give us A multiplied by BW. A multiplied by BW. Get that now? Now, this gain bandwidth product is something that must be constant for an amplifier, whether the amplifier is open loop or closed loop amplifier. You remember open loop and closed loop amplifier. Open loop means there is no feedback connected, and then there is no control over the output of the amplifier. But when you have a closed loop amplifier, you have feedback connected. And the feedback connected is ensuring that the amplifier is controlling its output. Now, when a negative feedback is applied to an amplifier, what is the effect on the gain? We all know that the gain reduces. The gain reduces. But what happens to the bandwidth? Of necessity, the bandwidth increases. The bandwidth increases. Now, the gain bandwidth products of an amplifier before and after feedback must remain the same. It must remain the same. Now, let us look at what effect does the negative feedback have on the lower frequency and the upper frequency, the lower sideband frequency, upper sideband frequency that we have. So let's frequency F1 equals F1 is a lower 3 decibel frequency, F2 is a upper 3 decibel frequency that we have it as we have it here. Now, after the feedback, we want to represent the frequencies with in notation. We have F1 prime and then F2 prime, whereby F1 prime is the lower 3 decibel frequency after feedback, and then F2 prime is the upper 3 decibel frequency after feedback. So the amplifier with feedback affects those frequencies in this manner. Look at what we have here. F1 prime equals F1 divided by 1 plus beta A. And then F2 prime equals F2 multiplied by 1 minus beta A. If you look at this formula critically and compare with F1 and F2, you will realize that F1 that we have here is higher in value than F1 prime, because F1 is being divided by a number, 1 plus beta A. Remember, beta A is always a number greater than 1. Beta A is a number greater than 1. And so, for that reason, beta A, 1 plus beta A is also greater than 1, such that F1 divided by 1 plus beta A is actually less than F1. So we have it that F1 prime is actually less than F1. All right? Okay. Now let's look at the second one. The second one is F1, F2 prime. F2 prime. Let's look at the effects of the amplifier on F2 prime now. Now F2 prime equals F2 multiplied by 1 plus beta A. Remember, 1 plus beta A is a number greater than 1. It's always greater than 1 because beta A, no matter how small it is, you can have it as 0.001, 0.1, whatever. Even though it is less than 1, but it's always greater than 0. So 1 plus beta A is always greater than 1. For that reason, F2 prime will be larger than F2 because F2 will be multiplied by 1 plus something, which is actually greater than 0. So we're going to have F2 prime is larger than F2. Thus, the amplifier causes a reduction of the lower sideband frequency, 3 decibel frequency. F1 prime is lower than F1, but F2 prime is higher than F2. That's what we have. So F2 prime is larger than F2, but F1 prime is smaller than F1. Therefore, like we said for a particular amplifier, the gain bandwidth product must remain the same. Therefore, A multiplied by BW, is equal to A prime multiplied by BW prime. And you remember what A prime is. A prime is actually the gain of the amplifier after feedback. So you could see it now. A multiplied by BW equals A prime multiplied by BW prime. Or you can rewrite it this way. A multiplied by F2 minus F1 equals A prime multiplied by F2 prime minus F1 prime. And that shows that an increase in bandwidth. Bandwidth has increased. That is what we can demonstrate in this graph now. Look at the screen now and see this graph. This is the original graph that we have. The one that has A up here. That was the original graph that we had up there. Now, after negative feedback, we now have this second graph down here. This second graph down here, which is now combined with it. Now, we look at this second graph, you now see that we have A prime here. A prime here is actually less than A along the axis. It's smaller than A. And then when you look at the horizontal axis here, you see that F1 prime is smaller than F1. And then F2 prime is higher than F2. That's what we have on the graph. Now, when you look at the bandwidth, the initial bandwidth when the amplifier was open loop is A. Look at the bandwidth, that is BW prime. After the negative feedback, you see that BW prime is actually larger than BW. Is that not so? Okay, I know you can observe that. If you observe this section now, you will see that BW prime is larger than BW. And that actually is the effect of negative feedback on the bandwidth. So the summary is that negative feedback increases the bandwidth of an amplifier, and that's an advantage, a big advantage rather. Despite the fact that the gain of the amplifier reduces from this value A to this value A prime, but that reduction in gain comes with a proportional gain in bandwidth. A proportional gain in bandwidth. Bandwidth, this is the original bandwidth here. This is original bandwidth. Now look at the bandwidth after negative feedback here, larger than the original bandwidth. That's a very good advantage of negative feedback on an amplifier. So let us exemplify what we have here. In that example, let us exemplify what we have there by means of an example. By means of an example. So we want to see how we can apply that knowledge that we have in an example to do some calculation. Okay. Example 6. An RC coupled amplifier has a mid-frequency gain of 200 and a frequency response from 100 Hz to 20 kilohertz. There's an error here again. Okay. Let us see the one we have here. Okay. Let's see what we have. I hope you have your notes open with you also. So let's look at my screen now to check my own notes. See my notes now. Now look at the example 6. Example 6. Okay. Right. This is correct now. An RC coupled amplifier has a mid-frequency gain of 200 and a frequency response from 100 Hz to 20 kilohertz. A negative feedback network with beta equals 0.02 is incorporated into the amplifier circuit. Determine the new system performance. I like this question. They didn't actually tell us what to calculate. They didn't tell us what to calculate, but what to calculate is what we are going to know now. Basically, the system performance depends on the gain and the bandwidth. The new system performance depends on the gain and the bandwidth. So after the negative feedback is applied, there will be a new gain and then there will be a new bandwidth. So we want to calculate that. Then we are going to check whether the gain multiplied by bandwidth before feedback is equal to gain multiplied by bandwidth after feedback. That is what we are going to determine. I know you are following. I see 8 of you in attendance in class. So just continue to follow me. Your microphones are muted. Until later on when I want you to ask questions. I will allow you to use your microphone. I will unmute from here. Okay. So just let us continue what we have there. We want to solve the amplifier performance. We want to get the amplifier performance after the negative feedback has been applied. That is what we want to do. Okay. All right. So let us go back to the screen and let us check the notes. I want to check the notes once again on the screen. So I will share the screen again. Okay. All right. We go back to the position we have, the example. Effect of negative feedback on the amplifier. This is the example now. Now let's look at the solution. Solution. A prime, that is the gain of the amplifier after negative feedback, equals A divided by 1 plus beta A. And that is 200 divided by 1 plus 4.02 times 200. You look at the question, we are told that the gain of the amplifier is 200. That is gain without feedback. And the frequency response is this, 100 Hz to 20 kilohertz. That is lower frequency and upper frequency, 120 kilohertz. And the feedback network has beta equals 0.02. That is a feedback factor beta is equal to 0.02. So we can now substitute those values into the equation here, and this is what we have. The answer is equal to 40. A prime is equal to 40. You can cross-check that one on your own calculator. That is correct. Right. Now let's look at the performance now. We are looking at F1 prime. F1 prime equals F1 divided by 1 plus beta A. 1 plus beta A. So when you substitute those values into this equation as well, F1 is 100. F1 is 100 here. That is lower 3 decibel frequency. 100 divided by 1 plus 0.02 times 200. That gives us 28. 28. Now F2 prime. F2 prime is equal to F2 multiplied by 1 plus beta A. So we substitute then again into the formula. We have 20 kilohertz multiplied by 1 plus 0.02 times 200. Now here we wrote 20 here. It's actually 20 kilohertz from the question. It's not 20 hertz. So for that reason, the answer we're going to get here, we're going to put kilo with it. Otherwise, if you don't want to do it that way, you could write 20 times 10 raised to the power 3 here. 10 raised to the power 3. You can add it, and then you will get 100,000 as your answer. So the answer is 100 kilohertz. 100 kilohertz. Now let's look at the BW prime. This is BW prime. You can change it to BW prime. That is F2 prime minus F1 prime. That is about, let's see, we have 100 kilohertz here. Here we have 20 hertz. So 100 kilohertz minus 20 hertz is approximately 100 kilohertz. Approximately, because it's 99.98 something kilohertz. So approximately, we could say the answer is 100 kilohertz. 100 kilohertz. Now we can show that the gain bandwidth product remains constant. How can we show that? The initial bandwidth, we represent that one with DW here. Initial bandwidth is F2 minus F1. F2 given initially was 20 kilohertz and the F1 was 100 hertz. If you do the calculation here, you say 20 kilohertz minus 100 hertz, you get something approximately 20 kilohertz. So I want you to go through that one, look at the screen carefully, and then see what we have here. See what we have there. Check in your own calculator. Confirm that it is correct. Yes, confirm that is correct. Okay, I think you have checked the example, you have checked the solution in your own calculator, you find out that the solution is correct, is accurate. Now, you will realize that this is not exactly 20 kilohertz. Check the screen again. This DW is not exactly 20 kilohertz because it's 20 kilohertz minus 100. That's about 19.9 kilohertz. But approximately it is actually 20 kilohertz. So we can now say that the gain bandwidth product will be equal if you use that values. A multiplied by first bandwidth, that's DW, is equal to 200 times 20. That's 4,000 kilohertz. And the A prime multiplied by DW prime equals 40 times 100. That is 4,000 kilohertz. So it's very interesting, isn't it? So the gain bandwidth product remains the same. And then we are able to calculate the system performance. The system performance include the gain after feedback, the lower frequency after feedback, and the upper frequency after feedback, then the bandwidth after negative feedback. So you see that that is very interesting. ADW is equal to A prime DW prime, as we have here. So that is that. Now we move on now to the next. Later on, we allow you to ask questions. But for now, let's continue with the explanation in the notes. We're moving on to the next subheading: negative feedback using operational amplifiers. Negative feedback using operational amplifiers. Operational amplifiers, or what we normally call op-amp. Op-amp. They are amplifier, they are integrated circuits actually. Integrated circuits inside which there are many transistors, resistors, and so on that have been wired together in order to actually achieve a particular gain of the amplifier. And you know the gain of the amplifier is A, or what we call AV, voltage gain. We'll be using A all along in these notes. So we still retain that value A as gain of the amplifier. But it is the same thing when you check some other notes or textbook, you will see AV, what they call voltage gain. So the operational amplifier has a gain A, but it's not only one transistor. It's not a single stage of transistor that is doing the amplification. They have several stages of amplifier wired together inside the integrated circuit called operational amplifier. Okay, now if the operational amplifier is connected as an inverting amplifier, then a signal can be applied to the non-inverting inputs as shown down here on the screen. Check the screen now. We have the operational amplifier here. Now, there are two terms I just used now that you need to take note of with an operational amplifier. An operational amplifier has two inputs and then one output. And that is why you see the symbol like a triangle, like an isosceles triangle kind of. And then here at this side, we have minus and positive at this side. So the minus and positive, those are the two terminals, two input terminals. The minus terminal there is the inverting input of the amplifier. And the positive terminal is the non-inverting input of the amplifier. And out here, we have the output. You can see V out here. That is where the output is. From the output is collected from the amplifier from here. V out. That is the output of the amplifier. So the amplifier basically has two inputs, one output. Meanwhile, this is just the simplified diagram of the amplifier. The amplifier has other legs, but these three legs are what we deal with when we are handling input and output. The other legs are for power supply. We have positive power supply and negative power supply to the amplifier, but that one is not our concern now. So just leave that one out of the diagram. So the inverting input is the input that has minus here. So anything that comes into this inverting input, where the amplifier will ensure if you are supplying a signal to the amplifier from that point, the signal will be amplified based on the difference between the two terminals, minus and plus. It will check the difference between the two terminals. Whatever the difference is, then it raises it up by value of gain. Meanwhile, if the input is actually entering from minus here, it means the amplifier will make sure that the result is inverted in sign. That is to say, if you are sending in positive voltage from minus here, the positive voltage will be amplified one, then it will be turned to negative at the output here. That's the point. So the negative voltage, if you are sending in negative voltage here, first of all, whatever the value is that enters the amplifier will be raised up by a gain A, then the total value, whatever raised up, will be inverted in sign. So if it was negative before, it will become positive at the output. On the other hand, if you are sending signal into the amplifier from the positive terminal, that is non-inverting input, the amplifier will check what is the value of the other terminal and then look at the difference. The difference between the two will be raised up by means of the gain of the amplifier A. but the value will remain as positive. If it is positive that came in, it will remain as positive as outside. If it is negative that came in, it remains as negative as outside. The amplifier will not invert the value, the sign. And that is why they call this one non-inverting input. And the other one here that has minus is called inverting input of the amplifier. I hope you get that. Fine. Now, like I said, the amplifier looks at the difference between the two terminals here. Whatever the difference is, then it will raise it up. It will raise it up for you. Okay? In 10 minutes time, the meeting may time out. The Zoom meeting may time out. So let's continue. If it times out, then we are going to log in again with the same meeting ID and password. Okay, let's continue. The negative terminal there, the positive terminal, they take in signal to the amplifier. The amplifier now checks what is the difference between the two. If you are putting in from here 2 volts, and from here you are putting in 3 volts. So the amplifier checks what's the difference between the two. So it will be 3 minus 2, and that is 1. So it means the 1 is entering from positive here because here is higher. The positive voltage is higher than the negative voltage. So that 1 will enter through V in plus, the input terminal plus. Now, that 1 will be raised up by the gain of the amplifier. If the gain of the amplifier is 400, then the output voltage that you are going to get will be 400 times 1. So you're going to get 400 volts. If it is positive, it will be positive outside. If it is negative in the input, it will be negative outside. Now, if you send this signal to this amplifier that we have here, it is a specially wired op amp. This is not the structure of op amp. We have a feedback connected now from the negative terminal to the output. It means that the output voltage can be taken back as a signal to the input here, to the inverting input. In that case, we are going to have a negative feedback on this operational amplifier. From B output, there is a terminal here that is connected back to the negative input, that is the inverting input. So when you have that, the output voltage of the amplifier will closely follow the input voltage. It will be following the input voltage at Vin. Because as it is now, we have wired the device up as a negative feedback amplifier. That become a negative feedback amplifier. So for that reason, whatever happens at the input will be controlled at the output because of the wiring that we have here. So as the voltage at the input increases, the out will also continue to increase. And then it is the differential gain that we will now observe at the output. The differential gain, when we say differential gain, we're talking about the difference between the two inputs, then multiplied by the gain of the amplifier, and that's what we are going to get at the output. However, if you continue to increase the input voltage, V out continue to increase, but it will get to a point when the output voltage will be stabilized. It will not increase anyhow again. Okay. So let us see whose mic is making. Okay, we want to mute everybody. So let your phone be muted. Okay.
That was okay. I can hear you.
All right. Okay. So we continue with our explanation here. So a point will be reached when the output voltage of that amplifier, will continue nearly equal to V in, but just low enough so that there are enough voltage difference left between V in and the inverting input. And that is amplified to generate the output voltage. Now, at a point, the output will not increase again. No matter how much you increase the input, At that point, the amplifier reaches what we call a stabilized state or equilibrium. And that is what we want to achieve by that wiring. The amplifier reaches a stabilized state whereby the output does not increase large enough again. It's now steady at a point. It means you have achieved stability by means of that negative feedback wiring of the amplifier. You have achieved stability. Now, that output is just the right amount of output to maintain the right amount of differential, which means that the right output voltage has been, produced.
Yeah, I hear you.
So what we have achieved actually is actually a negative feedback. We have actually achieved a negative feedback using the operational amplifier inputs, the non-inverting input and inverting input, such that the inverting input is connected directly to the output, and the input voltage is taken to the amplifier, is fed to the amplifier through the non-inverting input. That wiring is negative feedback that we have there. Now, that operational amplifier that we have there, like I told you, it has a gain called A, voltage gain A. That voltage gain A for operational amplifier is a very high value because the operational amplifier is actually an integrated circuit that has so many stages of amplifiers inside. So, for instance, the operational amplifier 741 that has the number 741 is a standard operational amplifier that has a very large gain. For instance, the gain of the operational amplifier 741 is up to 200,000. 200,000, and that is 106 decibel. And as you know, with all amplifiers, the gain of the amplifier can be determined with this formula that we have on the screen. AVOL equals V out divided by V in. That is, the voltage gain A is equal to output voltage divided by input voltage. Now, for a typical 741 operational amplifier that has about more than 200,000 gain, when you send in only 1 millivolts, what will you get at the output? You will get up to 200 volts. 200 volts. And that will actually make the operational amplifier to saturate quickly because the amplification is so high. But the thing is that in that open loop case, the amplification will be high, really, but it will be so unstable. It will be fluctuating. The output voltage will be fluctuating. So for that reason, we need a negative feedback. Negative feedback will, number one, reduces the gain of the amplifier. Number two, it ensures high stability. It does not allow the output voltage to fluctuate anyhow. Okay, and that is a very good advantage. Creates stability, high stability, even though the gain of the amplifier is reduced. So the use of negative feedback improves the performance of an operational amplifier. And any operational amplifier that does not have a negative feedback is regarded as an unstable amplifier, and it will be not really be useful in circuits because the output will fluctuate so much. That is why negative feedback is an advantage, despite the fact that it reduces the gain of the amplifier. It's an advantage for the amplifier. So that is how we can wire it, like we show it above. Wire the amplifier in this manner to achieve negative feedback. The inverting input, the negative terminal input, is connected directly to the output terminal. And then your signal that you want to amplify is fed in through non-inverting input. That is the positive input. So the amplifier is connected as negative feedback amplifier in that manner. But we need to actually introduce some circuit elements to ensure this feedback is connected. Yes. So we don't normally connect the wires directly like we have up there, but we wire it like this example that we have on the screen now. We have the screen now, we have the amplifier gain A, which is an operational amplifier, and then we have the non-inverting input terminal plus here, and that is where the input voltage is being applied, V input. Now, we have the V output, and then the inverting input terminal is connected to the V output by means of resistance R1, and that connection forms the feedback loop. That forms the feedback loop. Okay, so when you look at the screen now, you see that the operational amplifier has been wired as a negative feedback with the resistors needed. The gain of this operational amplifier is about 320,000. Look at it up here.